Welcome. Take a moment to settle in without trying to find the perfect position. Turn the volume down to the point where my voice is only just audible, a little below what would be comfortable in daylight. Nothing that follows needs to be remembered or understood or followed to the end. You can fall asleep at any point, and you will not miss a thing. Tonight we are going to talk about islands, slowly, without hurrying. Land with water all the way around it seems, at first, like one of the few ideas in geography that needs no explanation. And for the majority of the world's islands, the description holds without argument, since a small boat can be rowed around them and the water never runs out. Trouble appears at the margins, where the ground is low or minute or joined to something larger for part of the day. And it is along those margins that surveyors, cartographers and lawyers have had to write rules, because a rock that qualifies as an island may carry with it rights over a wide stretch of sea, while a rock that fails to qualify carries almost none. The tide supplies the first complication, since the shoreline of any coast is not a line at all, but a band that the sea crosses twice a day, and a patch of sand or reef that stands clearly above the water in the morning can be entirely covered by afternoon. Modern practice settles the matter by fixing on the upper limit of that band. Under the United Nations Convention on the Law of the Sea, an island is defined as a naturally formed area of land surrounded by water which remains above water at high tide, and everything hinges on those last four words. Ground that emerges only at low water has its own category and its own name. Charts describe such features as low tide elevations, and mark them with the drying heights that tell a navigator how far above the sea they will stand at the lowest states of the tide. Sandbanks in estuaries, coral flats inside a lagoon, reefs off a rocky headland. All of these appear and disappear on a rhythm set by the moon, and none of them counts as an island in the legal sense, however solid they look when a boat is anchored beside them at slack water on a spring low. Which high tide, though, is a question that different nations have answered differently, and the answer changes the tally of islands along their coasts. Some hydrographic offices work from mean high water, others from mean high water springs, others again from the highest astronomical tide, the greatest level predicted from the combined pull of sun and moon over the full cycle of their motions. Where the tidal range is a few tens of centimeters, as in parts of the Mediterranean, the choice hardly matters. In the upper reaches of the Bay of Fundy, where spring ranges exceed 15 meters, the choice governs whether a considerable amount of rock and mud belongs to the land or to the sea. Two further words in the legal definition do quiet work. Because the land must be naturally formed, the harbour walls, dredged platforms and reclaimed terminals that stand permanently above the highest water do not become islands by standing there, and cannot generate the maritime zones that natural land generates. The convention adds a further distinction, setting aside rocks which cannot sustain human habitation or economic life of their own, and denying them an exclusive economic zone or continental shelf, while leaving them a territorial sea. A granite pinnacle in the North Atlantic named Rockall, rising perhaps 20 meters from deep water, is an island by the physical test and a rock by the economic one. And the United Kingdom in the end gave up claiming a broad zone of sea from it. Coastal geography adds cases the law was never written to settle. Mont Saint-Michel in Normandy and Lindisfarne off the Northumberland coast are both surrounded by water at high tide and both reachable on foot when the sea withdraws. One across a causeway, the other along a marked crossing that floods on schedule and drowns the occasional unhurried visitor. Naturalists and administrators have treated these places as islands for centuries, on the grounds that the tide, not the road, decides. A built causeway that never floods produces the opposite outcome, and the island quietly becomes a promontory in everything but name. Fresh water raises a separate and largely unresolved matter of bookkeeping. The plain definition says nothing about salinity, so an 8 in a river, a wooded knoll in a reservoir, and the granite lump in the middle of a Finnish lake all satisfy it. And national inventories that include them arrive at figures far larger than any purely coastal count. Nordic surveys of this kind run to the hundreds of thousands. Elsewhere, the same features are excluded as a matter of habit, so that comparing the island count of one country with that of another often compares two different questions rather than two coasts. Even for the sea alone, counting depends on the fineness of the map. A coast is irregular at every scale examined, so a chart drawn at 1 to 1,000,000 shows a handful of offshore islands, where a chart at 1 to 50,000 shows several hundred, and a low-altitude aerial survey of the same water finds skerries and washing rocks that no chart had troubled to record. Norway's fretted outer edge and the archipelagos of the Baltic behave this way at every level of detail. Any published total therefore carries an implied threshold, some minimum area or minimum height below which a lump of rock is not worth an entry, and the threshold is usually left unstated. Area is measured with rather more agreement than number. For most of the 19th and 20th centuries, the work was done with a planimeter, a mechanical instrument traced around an outline on a map to give the enclosed area by the motion of a wheel, and the results were only ever as good as the survey underneath. Digital coastline datasets and satellite imagery have replaced the tracing, though the underlying difficulty remains, since the outline still has to be chosen at some level of resolution and referred to some tidal datum before the figure means anything. Ice complicates the largest case of all. Greenland's ice sheet buries the rock beneath it and presses much of the interior bedrock below sea level, so the coastline that appears in atlases is the edge of ice as much as the edge of stone in some places. And geologists have long observed that the same land unloaded of its ice and left to rise again over thousands of years would not present the same shape at all. As measured today, Greenland covers a little over 2 million square kilometers, which is more than twice the area of the next island in any ranking. Australia, at roughly 7.5 million square kilometers, is some 3.5 times larger and is not called an island. The definition of an island sets no upper bound on size, and by the letter of it, Australia surrounded by ocean qualifies as neatly as any sandy cay. What excludes it is a separate convention entirely, one that treats continents as a small set of primary landmasses agreed by usage and supported by geology. And Australia rests on its own continental plate, sharing a shallow shelf with New Guinea and Tasmania that was dry ground when sea levels stood lower. Greenland, by contrast, lies on the same plate and the same ancient continental crust as North America, and is read as a piece of that continent rather than a continent in itself. Conventions of this sort are agreements rather than findings, which is why the number of continents taught in schools varies between 6 and 7 depending on the country, and why the boundary between Europe and Asia follows a line negotiated across the Urals instead of a strait. The same tolerance for convention explains the treatment of canals. Since 1869, a ship has been able to pass through Suez, and since 1914 through Panama, so that Africa and the Americas are each severed from their neighbors by a navigable channel. Yet no atlas records the resulting islands, because the cut was made by dredgers and the definition asks for land shaped by nature. Ranked by area, the roll of islands drops away steeply from its head, so that the first 5 names hold more ground between them than the following 40. Greenland stands near 2,100,000 square kilometers. New Guinea somewhere close to 785,000. Borneo a little under that, Madagascar around 587,000, and Baffin Island in the region of 507,000. The interval between the first and the second is itself wider than any other island on the planet, which gives the list a shape unlike most geographical rankings, top-heavy and then gently sloping. Sumatra follows Baffin, then Honshu, Victoria Island, Great Britain, Ellesmere and Sulawesi, and by the time the tally reaches its 20th entry, the figures have fallen to a fraction of Greenland's. Order in the upper part of the list has been stable for a century, though the numbers attached to each name have not. Each of those areas rests on a decision about where the land is judged to stop. A coast is not a line, but a zone that shifts with the tide, and a figure quoted to the nearest square kilometer conceals a choice of tidal datum, a choice of scale, and a choice about whether to count the sandbars and deltas that migrate from one decade to the next. Greenland presents a further complication since much of its edge is glacier front rather than rock, and glacier fronts advance and retreat. Areas published for the island therefore differ by tens of thousands of square kilometers depending on the source and the year, and the honest version of the number is a range. None of this disturbs the ranking because the gaps between the leading islands are far larger than the uncertainties, but it explains why 2 atlases printed in the same decade rarely agree to the last digit. Greenland's outline was assembled over roughly 1,000 years, and in an uneven order. Norse settlers knew the southwestern fjords from the 10th century onward and sailed north along that shore to hunt, while the east coast, guarded by a belt of drifting pack ice, resisted approach far longer, and whalers working the Davis Strait filled in the western bays piece by piece as the fishery drew them higher. Danish trading stations established in the 18th century gave fixed points from which the western coast could be charted with some consistency. Beyond about 76 degrees north, the record thinned, and the whole northern quarter of the island remained a matter of guesswork on charts printed well into the 19th century, with cartographers sometimes leaving the top of Greenland unfinished, and sometimes joining it to a supposed polar land. Sledges completed what ships could not reach. Because the interior is buried under an ice sheet covering about 4/5 of the island, up to some 3 kilometers thick at its crown. The only practical way to trace the northern shore was to travel across ice with dogs and depots, taking astronomical positions when the weather allowed, and dead reckoning between them. Fridtjof Nansen and a small party crossed from the east coast to the west in 1888, proving that the ice sheet was a single continuous dome rather than a mountainous unknown. In the following decade, sledge journeys reached the northern coast, and showed that it closed, settling the question of whether Greenland was an island at all. A Danish expedition wintering in the northeast between 1906 and 1908 mapped the last unvisited fjords, and 3 of its members died on the return. Aerial photography altered the pace entirely. Once aircraft could be flown from ships or from coastal strips, a single season's flying yielded overlapping vertical photographs of shorelines that had cost sledge parties whole winters. And Danish expeditions of the 1930s began photographing the East Greenland coast from the air on that principle. Stereoscopic pairs viewed under a plotting instrument gave relief as well as plan, so that fjord walls and nunataks could be drawn without anyone standing on them. Ground control was still needed, since photographs alone cannot supply scale or absolute position, and survey parties continued to occupy stations along the coast to fix the framework into which the imagery was fitted. The northern islets remain unsettled in one small respect, because gravel banks off the north coast appear and disappear, and the title of the world's northernmost land has changed hands more than once. New Guinea reversed the usual sequence, its coast becoming familiar long before anyone understood the country behind it. Portuguese and Spanish ships sighted the northern shore in the 16th century. Dutch vessels traced much of the western and southern coasts in the 17th, and in the 1620s, a Dutch navigator recorded snow on a mountain range close to the equator, a report treated in Europe as an error for generations afterwards. Charts showed a reasonable outline while the interior stayed blank, partly because the island's spine rises above 4,000 meters, with the highest summit near 4,880, and partly because ridge after ridge of forested limestone and volcanic rock lay between the coast and anywhere else. Patrols in the 1920s and 30s, guided in part by reconnaissance flights, found broad grassland valleys in the eastern highlands carrying dense farming populations that no map had recorded. On Borneo, the rivers did the work of roads. Dutch surveyors advanced from the southern and eastern coasts, British administrations from the north. And in both cases, the practical route inland was by boat up the Kapuas, the Barito, the Mahakam or the Rajang, sounding and sketching as the parties went, with positions carried upstream by compass traverse and checked against astronomical observations at settlements. Triangulation in lowland rainforest is slow, since a theodolite needs sightlines and the canopy offers none, so towers had to be built or hilltops cleared for each station. Cloud, which sits over much of the island for a large part of the year, delayed the aerial coverage that had gone quickly elsewhere. Radar, which sees through cloud and is not troubled by darkness, eventually supplied the missing sheets, and later satellite passes tied the whole island into one geodetic frame. Madagascar had been drawn in fair proportion long before its interior was understood, because the island lay beside the sailing route to India and every passing squadron had reason to know its capes. Portuguese, Dutch, English and French navigators charted the coast across the 16th and 17th centuries, and its length of roughly 1,600 kilometers was known within tolerable limits when the highland plateau was still described from hearsay. Missionaries and travelers of the 19th century supplied routes and rough heights, while a systematic topographic survey followed French administration at the close of that century, laying out baselines and triangulation networks across country that ranged from rainforest escarpment to dry spiny thicket. Aerial coverage flown in the middle of the 20th century brought the whole island onto consistent sheets, and the eastern coast, long and nearly straight, proved to be one of the simplest lines in the tropics to plot. Baffin Island carries the name of an English navigator who sailed into the bay beyond it in 1616, and its charting followed the fortunes of the whale fishery and the search for a northwest passage. Voyages after 1818 fixed much of the eastern shore with its deep fjords and mountain wall, while the western side, facing the shallow and ice-choked waters of Fox Basin, stayed sketchy for another century. Interior lakes were known from Inuit accounts before any surveyor saw them, and Franz Boas, wintering on the island in the 1880s, combined his own traverses with maps drawn for him by Inuit hunters. Canadian aerial photography after the Second World War finished the outline, closing the western bays and the low, marshy islands of the basin, and with that, the fifth largest island on Earth acquired an edge that has not needed serious revision since. An island's outline can be finished on paper long before anyone asks what the island is made of, and the two inquiries have separate histories. Coasts were drawn by navigators with sextants and lead lines, while the rock underneath was read much later by geologists who came ashore with hammers and notebooks and worked inland from the beach. That later reading divided the world's islands into groups that have nothing to do with size. Some were built where they now stand, raised from the seafloor by volcanoes or accumulated as limestone by living reefs. Others are older than the water around them, being pieces of continental crust that carry the same gneisses, granites, and folded sedimentary sequences as the landmasses they once formed part of, left offshore when the crust between thinned, stretched, and finally parted. Madagascar belongs firmly to that second group. Across the eastern and central portions of the island, which together make up most of its area, the surface rock is crystalline basement, gneiss and schist and granite that formed and were reheated deep in the crust over a span reaching from nearly 3,000 million years ago to about 500 million years ago. 19th century travelers noticed the character of this ground without being able to date it, describing red lateritic soils over hard grey rock, bare domes rising above the plateau, and quartz veins in the stream gravels. Systematic mapping in the 20th century divided the basement into belts with distinct histories, and those belts do not stop at the shoreline. Their counterparts run on in Tanzania and Mozambique to the west and in southern India and Sri Lanka to the east, matching in age, in metamorphic grade, and in the direction of their internal grain. Along the western third of the island, the picture changes. There, the basement is buried beneath sedimentary basins whose lowest beds record glaciers, then coal swamps, then sandy river plains, in a sequence closely comparable to the Permian and Triassic strata of southern Africa, laid down when the two regions were one continuous interior. Marine limestones and shales appear above them, and their arrival marks the moment when seawater entered the widening gap. Rifting began in the Jurassic, roughly 160 million years ago, and Madagascar moved southward relative to Africa along a great fracture zone that still shows on the floor of the Mozambique Channel as a long north-to-south ridge. By about 120 million years ago, that motion had stopped, and the island has occupied approximately its present place with respect to Africa ever since. India remained attached for another 30 million years or so, joined along what is now Madagascar's eastern coast, the long straight edge that proved so easy to chart. Separation came in the late Cretaceous, near 88 million years ago, and it left matching traces on both sides. Basalt flows and intrusions of that age in southern Madagascar, and rocks of similar age and composition on the Indian side. A pairing generally linked to the passage of a hotspot beneath the rift. The straightness of the eastern shore is a consequence of this, a rift margin trimmed by faulting rather than a coastline worn into bays. Fossil evidence supported the same conclusion before the plate movements were quantified, since Madagascar's Cretaceous dinosaurs and freshwater vertebrates resemble those of India and South America more closely than anything living on the island since. Farther north in the same ocean, the granite islands of the Seychelles present continental rock, in a setting where it seems least likely. Mahé, Praslin and La Digue are built of coarse granite with large feldspar crystals, weathering into rounded boulders that pile along the beaches, and the rock has been dated to roughly 750 million years, a figure with no relation to the surrounding sea floor. No volcano lies beneath them. The islands sit on a shallow bank of thinned continental crust that was carried away from the Indian margin around 60 million years ago, during the episode of enormous basalt eruption that covers much of western India, and they have stayed there, several hundred kilometers from any other land, as a splinter of a continent that broke twice. New Zealand posed a related problem on a larger scale. Its rocks include Paleozoic and Mesozoic sandstones and mudstones folded and hardened into grey waka and schist, together with granite bodies in Fiordland and Nelson that correspond in age and chemistry to granites in eastern Australia. So the continental character of the two main islands was never in doubt. What took longer to establish was how much continental crust lay around them underwater. Bathymetric charts built up through the 20th century showed broad, shallow platforms rather than open abyss. The Campbell Plateau to the south, the Chatham Rise to the east, the Challenger Plateau to the west, and the long Lord Howe Rise and Norfolk Ridge running away to the northwest, most of it lying between a few hundred and about 1,500 meters below the surface, which is far too high for ocean floor. Dredging settled the composition. Hauls from those ridges brought up granite, quartz sandstone, coal fragments and limestone containing the shells of shallow water animals, rather than the basalt that covers ordinary seafloor, and later drilling into the northern rises recovered sediments deposited near a coast. Seismic refraction measurements gave crustal thicknesses of about 20 to 30 kilometers under the plateaus, against something near 7 kilometers for typical oceanic crust, thinned continental rock rather than anything oceanic. Added together, the emergent and submerged parts amount to roughly 5 million square kilometers, of which some 94% stands below sea level, with New Zealand, New Caledonia, and a scatter of smaller islands including the Chathams, the Aucklands and Campbell Island making up the remainder. A single name for the whole mass, Zealandia, came into use from 1995, and a detailed case for treating it as a continent in its own right was set out in a scientific paper published in 2017. Its history follows the general pattern. Stretching of the crust began somewhere around 100 million years ago, Seafloor spreading opened the Tasman Sea between roughly 83 and 52 million years ago, and the stretched block subsided as it cooled, sinking gradually beneath the water it had displaced. The land that stands above the surface today owes much of its height to a later cause: the collision and shearing along the boundary between the Pacific and Australian plates, which raised the southern Alps and continues to lift them faster than erosion can level them. Continental fragments survive in the far north as well, and there the interest lies in their age rather than their extent. Across the Outer Hebrides and along the mainland coast opposite, the ground is Lewisian gneiss, a banded grey rock whose oldest components approach 3,000 million years, and which was buried, heated and deformed repeatedly before being cut by later dikes. It weathers into a low, knobbly terrain of bare rock ridges and shallow lowcans, holding almost no soil, and the pattern of that landscape can be traced from the air across Lewis and Harris as clearly as any geological map draws it. Greenland's western coast carries rock of the same family and greater antiquity, including gneisses near the head of the fjords behind Nuuk, and within them the belt at Isua, where metamorphosed sedimentary and volcanic rocks have been dated at close to 3,700 million years, among the oldest surface rocks yet identified. Small islands offshore expose comparable material, so the oldest known ground on the largest island is also, by the convention that counts Greenland as an island at all, ground surrounded by sea. Similar reasoning applies in the South Atlantic, where the basement exposed at the southern tip of West Falkland has yielded ages near 1,000 million years, and the Devonian sandstones above it contain fossil shells matching those in beds of the same age in South Africa. Measurements of magnetization in the Falkland rocks have been interpreted as showing that the block rotated substantially as Gondwana came apart, which would explain why its strata lie at an angle to the trend they should share with their African counterparts. Across the floor of the North Pacific, a line of volcanoes runs away from the island of Hawaii toward the northwest, keeps that heading for some 3,500 kilometers, turns almost due north near the middle of its length, and carries on as a submerged ridge of flat-topped and rounded seamounts until it disappears into the deep trench off Kamchatka. The southeastern end of that line is land, high and unmistakable, with Mauna Loa and Kilauea erupting in living memory and Mauna Kea rising above 4,000 meters. The northwestern end is water, with nothing showing on the surface at all. Between the two extremes lies every intermediate stage, arranged in sequence, and the reading of that sequence became one of the clearer confirmations that the floor of the ocean moves. James Dwight Dana, who sailed with the United States Exploring Expedition and spent time in the Hawaiian group around 1840, noticed that the islands were not equally worn. Hawaii itself had smooth young slopes and fresh lava. Maui and Molokai were cut into by valleys. Oahu's mountains had been reduced to two ragged ridges facing each other across a plain. Kauai was gullied to its core and blanketed in soil. Since rain and surf work at much the same rate on similar rock in similar climate, the differences in wear had to be differences in time, and Dana concluded that volcanic activity had shifted along the chain, dying away in the northwest and continuing in the southeast. He had the direction and the order right more than a century before anyone could say why. Radiometric dating gave the sequence numbers. Measurements of potassium and its argon decay product in Hawaiian lavas, made from the 1960s onward, put the shields of Kauai at roughly 5 million years, those of Oahu between about 2 and 4 million, Maui's Haleakala at under 1 million with eruptions in the last several centuries, and Kilauea at a few 100,000 years and still building, carrying the same work northwest along the low reefs and banks. The ages climb steadily. Nihoa near 7 million, Necker above 10, Midway near 28. The reefs beyond it older still. Dividing distance by age difference gives a rate of about 8 or 9 centimeters a year, which matches, within the uncertainty of such things, independent estimates of how fast the Pacific Plate is traveling. John Tuzo Wilson set out the mechanism in 1963, in a short paper proposing that the source of the lava stays fixed in the mantle while the plate slides over it, so that each volcano is cut off from its supply as the crust carries it away and a new one begins where the plate now sits above the source. Jason Morgan extended the idea in 1971, arguing that such sources are the tops of narrow plumes of hot material rising from far down in the mantle and using them as reference points against which plate motions could be measured. Neither proposal required anything more exotic than a stationary heat source and a moving lid, and both made a prediction that could be tested by dating rock at intervals along a chain. Loss of height follows loss of activity, for two reasons that act together. A shield volcano is a heavy load on the crust, and the crust bends beneath it, so the island begins to settle almost as soon as it is built. Separately, the plate itself cools as it moves away from the heat source, contracts and rides lower. Rainfall and waves remove the top, while subsidence lowers the base. The result along the Hawaiian ridge is a graded series. Kauai and Niihau still substantial, Nihoa and Necker reduced to bare basalt crags of a few 100 meters and less, French frigate shoals down to a single pinnacle standing in a lagoon, and then Laysan, Lisiansky, Pearl and Hermes, Midway and Kure with no volcanic rock above water at all. Only rings and arcs of coral sand on limestone. Boreholes at Midway found basalt under a few 100 meters of reef limestone, confirming what the pattern implied. Kure is the last atoll. Northwest of it, reef growth can no longer keep pace with the sinking, partly because the water there is cooler and coral builds more slowly, and the drowned summits pass below the surface for good. Geologists have named that threshold after Darwin, since he had described the sequence of fringing reef, barrier reef and atoll without knowing the age order of the islands he was fitting it to. Beyond the threshold, the chain continues as guyos, seamounts whose tops were planed flat by waves when they were islands, and now lie hundreds or thousands of meters down, their old shorelines drowned in place. Drilling settled the northern half. In 1977, a leg of the deep-sea drilling project reached basalt in several Emperor seamounts, and the dates came out where the sequence said they should, with Suiko near 65 million years and the seamounts nearer the Aleutian Trench older again, approaching 80 million. Sampled sediments included shallow water debris and the remains of reef organisms, so these were islands once at the surface in warm water. A later expedition drilled Detroit, Nintoku, and Koko seamounts specifically to measure the magnetization of their lavas, which records the latitude at which each cooled. Those measurements complicated the tidy picture in an interesting way. Hawaii sits near 19 degrees north, and if the source had been truly fixed, every volcano in the chain should have formed at that latitude and then been carried away from it. Instead, the older Emperor seamounts recorded formation well to the north of 19 degrees, by something on the order of 10 degrees or more, with the discrepancy shrinking toward the younger end. The straightforward reading is that the hotspot itself drifted southward while the Emperor chain was being built, and then became more nearly stationary. Hotspots on this evidence are slow-moving rather than anchored, which affects how much weight their tracks can bear as a reference frame. At the bend, the change of heading takes place over a stretch of seamounts dated near 47 million years. For a long time, the turn was read as a change in the direction of Pacific plate motion, and there is supporting evidence in fracture zone patterns and in the record of the plate's boundaries elsewhere. The southward drift of the plume accounts for part of the geometry as well, and the current view distributes the cause between the two, with argument continuing about the proportions. Elsewhere, the same reasoning has been applied with the same result. In the Society Islands, Mehetia and Tahiti stand at the young southeastern end, while Maupiti and Bora Bora to the northwest are lower and further along in the reef sequence. The Canary group grows older toward Africa, with Lanzarote and Fuerteventura long since worn down, and La Palma and El Hierro still erupting. Réunion, high and active, lies at one end of a track that runs through Mauritius and Rodriguez, along the Chagos and Laccadive ridges to the flood basalts of the Deccan. The Louisville Ridge in the South Pacific and the Volcanic line across the Snake River Plain leading to Yellowstone are read the same way, one as a chain of seamounts, the other as a chain of calderas on land. Not every line of volcanic islands works like this. The Aleutians, the Kuriles, Tonga and the Lesser Antilles are arcs above descending slabs of ocean floor, where dozens of volcanoes are active at once along the whole length of the arc, and no age order runs from one end to the other. Distinguishing the two kinds of chain by dating their rock became in itself a way of telling which islands sit above a plate boundary and which merely sit on a plate. Southeast of Hawaii, roughly a kilometer below the surface, a submarine volcano called Lo'ihi in the older literature, and now more often given the name Kamaehuakanaloa, is erupting on the seaward flank of the chain. Should it continue, it will become the next island in the order, while Kilauea takes its place in the worn procession to the northwest. Reef-building corals are, in a strict sense, shallow-water animals. They carry algae in their tissues, and those algae need light, so the vigorous growth of a reef belongs to the upper 10 or 20 meters of water, thinning downward and effectively ceasing somewhere near 50 or 60 meters, in water that stays warmer than about 18 degrees Celsius through the year. That constraint is what made the atolls of the open Pacific and Indian Oceans a genuine problem for 19th century geology. A ring of living coral, sometimes 50 kilometers across, enclosing a shallow lagoon and surrounded on all sides by water 4,000 or 5,000 meters deep, cannot have grown from the sea floor. It must be standing on something. Charles Lyell, writing before any deep sounding had been made near such a ring, proposed that atolls were the rims of submarine craters, coral having settled on the circular lip of a drowned volcano. The suggestion accounted for the shape and for the lagoon, and it had the merit of using a known kind of landform. Its difficulty was scale. Volcanic craters of 30 or 40 kilometers in diameter are rare, and the atolls of the Marshall and Tuamotu groups came in a range of sizes that no crater population matched. Some of them elongated, some kidney-shaped, some with two lagoons separated by a bar of reef. A different answer came from a young naturalist who worked it out, by his own later account, on the western coast of South America, where he had been studying raised beaches and evidence of land slowly rising. If a coast could rise, a seafloor could sink. Darwin reasoned that a volcanic island in warm water would first acquire a fringing reef along its shore, that as the island subsided, the coral would keep growing upward to stay in the light, so that a channel of water opened between the reef and the retreating shoreline, and that the island would eventually vanish beneath the surface altogether, leaving the reef alone as a ring with a lagoon where the mountain had been. The sequence had a testable consequence, which was that all three forms should be found together in the same warm oceans, and that the intermediate stage should be visible. He saw one at Tahiti, where a barrier reef stands off from a high volcanic island with a lagoon between, and in April of 1836, the Beagle anchored at the Cocos or Keeling Islands, an atoll of the eastern Indian Ocean, where he sounded the outer slope and examined the coral rubble of the rim. His book on the structure and distribution of coral reefs appeared in 1842, with a world map on which fringing reefs, barrier reefs, and atolls were colored differently, and the distribution of atolls read as a map of regions of slow subsidence. Arithmetic supports the mechanism comfortably. A healthy reef can add centimeters of framework in a year, while the sinking of an old volcanic edifice as it cools and as the plate beneath it settles proceeds at something more like centimeters in a century. Coral does not merely keep pace, it can afford long interruptions and still recover the surface. The limestone that accumulates is not solid coral either, but a mixture of coral framework, cemented sand, the skeletons of calcareous algae, and cavities compacting under its own weight as the pile grows. Against this stood a rival account that took its evidence from deep-sea dredging. In the 1880s, working from what the Challenger expedition had recovered, John Murray argued that submarine banks could be built up from the sea floor by the steady rain of shells and skeletons of open ocean organisms until their summits came within reach of coral growth, after which the outer edge of the reef, better fed and better washed, would outpace the middle, and the center would be lowered by solution to form a lagoon. No subsidence was required. Alexander Agassiz spent years and a good deal of his own money visiting reefs across the Pacific and the Caribbean in the hope of showing that Darwin's explanation was unnecessary, and the argument between the two positions ran on without resolution because both could explain the visible surface. What separated them lay underneath. Settling it required a hole. Between 1896 and 1898, the Royal Society of London sent 3 expeditions to Funafuti, an atoll in what is now Tuvalu, with diamond drilling equipment and the intention of boring through the reef to whatever lay below. The work was difficult in ways the organizers had not anticipated. Loose coral sand collapsed into the hole, casing had to be driven down to hold the walls, the bit jammed in cavities. and the core recovery was poor in the porous upper sections. The deepest boring reached a little over 340 meters and was still in reef limestone and dolomite when it stopped. That result was read in both directions. Supporters of subsidence pointed out that shallow water limestone extending to 300 meters could only have been deposited near the surface and then carried down. Skeptics replied that the drill had not reached volcanic rock, so nothing had been proved about the foundation, and that dolomite and recrystallized limestone raised questions about how the succession had formed. The Funafuti cores were studied for decades afterward, and they are still studied, but they did not close the case. Two developments in the middle of the 20th century did. The first was geophysical. Seismic refraction surveys run across Pacific atolls, and their surrounding seafloor showed a relatively thin cap of low-velocity material over a basement with the velocity of basalt, and the shape of that basement under several atolls resembled a truncated volcanic cone. The second was deeper drilling. At Enewetak in the Marshall Islands, holes put down in 1952 passed through limestone all the way to basalt, in one hole at a depth a little beyond 1,200 meters and in the other closer to 1,400. An earlier hole at a neighboring atoll had stopped, still in limestone, at several hundred meters. What the Enewetak cores contained was as informative as the basalt at the bottom. The whole column was shallow water carbonate, deposited near sea level, with the oldest layers just above the volcanic rock dated to the Eocene, some tens of millions of years ago. A volcano had stood there, had been fringed by reef, and had gone down more than a kilometer while the reef built upward and stayed at the surface throughout. Drilling at Midway in the 1960s found the same arrangement: basalt beneath a few hundred meters of shallow water limestone at the far northwestern end of a chain whose age progression was by then being worked out. Darwin's account survived, but not untouched. Reginald Daly pointed out in the early 20th century that sea level itself had fallen by more than 100 meters during glacial periods, exposing reef limestone to rain and to dissolution and cutting flat platforms by wave action so that the present reef surfaces might owe their shape to those episodes rather than to steady sinking. Cories bear him out in the upper section. The living reef of a modern atoll is a thin post-glacial veneer, at most a few tens of meters thick, grown in the last thousands of years on an older limestone surface pitted and channeled by solution during the last low stand, and beneath that surface are further solution horizons, each marking a time when the top of the pile stood in the air. The islands that people live on, in the Maldives, in Tuvalu, in Kiribati and the Tuamotu, are not the reef itself, but banks of sand and coral shingle heaped by waves onto the reef flat, rarely more than 3 or 4 meters above the water, held together by vegetation and by beach rock. Their foundation runs down through a kilometer or more of limestone to the drowned basalt of a volcano that last stood in the sunlight long before anything resembling the present ocean chart existed. Almost every island on the chart is older than the charts themselves, older than writing, in many cases older than the human species, so that the geologist explains its origin from rock and structure rather than from any account of the event. A small number are exceptions. Within the period of instruments and logbooks, a few pieces of land have risen out of open water while people watched, were photographed from ships and aircraft, were sampled while still steaming, and were measured week by week as they either hardened into permanence or were taken apart again by the sea. These cases are worth attention less for their novelty than for what they show about the first few years of an island's life, a stage that is otherwise entirely inferred. The clearest of them lies off the southern coast of Iceland, beyond the outer edge of the Vestmannaeyjar, where the seafloor stands some 130 meters down. Early on the 14th of November, 1963, the crew of a fishing vessel working that ground saw dark smoke rising from the water and steered towards it, supposing at first that a boat was burning. What they found instead was a line of explosions breaking the surface, throwing ash and steam upward in bursts, and within a day, the disturbance had built a ridge of loose black material above the waves. The island was given the name Surtsey, after the fire giant of Norse tradition, and its eruption continued in various phases until June of 1967. Eruptions that break through shallow water behave differently from those on dry land, and Surtsey supplied the type example so completely that volcanologists still describe the style as Surtseyan. Seawater reaching hot magma flashes to steam and shatters the melt into fine fragments, and the fragments are then thrown out in dark, cypress-shaped jets that collapse and repeat every few seconds or minutes. The product is a cone of unwelded ash and cinder, permeable, uncemented, and no stronger than a heap of gravel. Cones of that kind form quickly and disappear quickly, since the North Atlantic swell can remove in a winter what an eruption spent a season assembling. Surtsey escaped that fate because the cone eventually grew wide enough and tall enough to seal water away from the vent, and in April of 1964, the activity changed character altogether, from explosive shattering to the quiet outpouring of lava. Fluid bale spread across the western side of the island and ran into the sea, building a resistant apron and a low shield that covered the loose tephra beneath. That armor is the difference between an island and a shoal. When effusion finally ceased, the land stood roughly 170 meters above sea level and covered something close to 2.5 square kilometers. Two smaller cones appeared nearby during the same episode, on separate vents along the fissure, and neither reached the lava stage. One rose in the spring of 1965, the other later that year, and the second, named for the midwinter feast, survived into the following summer before the waves reduced it to a submerged bank. They serve as the control experiment for their larger neighbor, since they were built of exactly the same fragmented ash and simply had no basalt cap. Surtsey itself has been shrinking since the day its eruption stopped. Cliffs cut back on the exposed southern and western sides, sand and boulders are carried round to form a spit on the sheltered flank, and surveys through the following decades recorded the area falling to roughly half its greatest extent, with the rate of loss slowing as the remaining ground came to be dominated by lava rather than by tephra. Inside the island, heat and circulating water altered the volcanic glass into a yellow-brown substance called palagonite, which cements the loose grains into a tough tuff. And this internal hardening has done as much for the island's survival as the lava on its surface. Boreholes drilled into the cone, first at the end of the 1970s and again several decades later, recovered cores showing how far that alteration had progressed and how the hydrothermal system inside a young volcanic island evolves. From its first days, Surtsey was treated as a scientific reserve, with landing restricted so that the arrival of life could be recorded without the confusion of introduced seeds and boot-carried spores. Bacteria and fungi were found early. The first flowering plant, a sea rocket on the shore, was recorded within 2 years. Mosses and lichens followed and spread over the lava, and gulls began to nest on the island in the 1980s, after which their droppings, feathers and dropped food accelerated the making of soil and the delivery of seeds. The island was added to the World Heritage List in 2008, less for its scenery than for that uninterrupted record of colonization. Roughly 1,000 kilometers south of Tokyo, in the volcanic arc that runs from the Izu Islands towards the Marianas. A different and longer performance has been going on at Nishinoshima. A small, weathered island had existed there for a long time, the exposed rim of a large submarine edifice, whose base lies some 3,000 meters down. In 1973 and 1974, new vents erupted just to the east of it and built an islet that eventually joined the older ground. And the enlarged island then sat quietly for about 4 decades while the sea trimmed the new material. Activity resumed in November of 2013 with a fresh cone a few hundred meters offshore, and this time the eruption produced lava steadily rather than in a single burst. The new cone grew, its flows spread outward, and by the end of that year, the growing mass had reached and then buried almost all of the earlier island, so that the entire visible surface became young rock. Episodes of renewed eruption followed at intervals through the second half of that decade, each adding to the coast and to the summit, and a vigorous period in 2020 raised the crater considerably higher and widened the island again. Because the material is largely lava rather than ash, the additions have been durable, and the shoreline retreats between eruptions without the whole structure being dismantled. Nishinoshima is uninhabited and difficult to approach, so almost everything known about its growth comes from aerial survey and satellite imagery, with the Japanese authorities publishing successive outlines and heights, and issuing navigation warnings when discolored water and floating pumice appear. Each enlargement slightly extends the territorial sea drawn around the island, which is one reason the surveys are as regular as they are. Cases that ended the other way are more numerous. In the summer of 1831, a submarine eruption in the Strait of Sicily, between the island and the Tunisian coast, threw up a cinder island that reached a height of several tens of meters and a circumference of some kilometers. It was visited, sketched, sampled, and claimed in short order by more than one government, under more than one name, and while the diplomatic correspondence was still being written, the sea flattened it. By early the following year, nothing remained above water, and the site is now a shoal lying a few meters below the surface, marked on charts as a hazard and as a place where eruptions have occurred. Similar appearances and removals have been recorded repeatedly in the Tonga Arc, where shallow submarine cones lie along a line of islands and reefs. One bank there has produced short-lived islands on several occasions since the 1980s, each of ash and pumice, each surviving months rather than years. Another Tongan volcano built a low neck of ground joining 2 older islets in the middle of the last decade, and that connecting land was largely destroyed in the violent eruption of January 2022. Which removed much of the visible island as well. In the southern Red Sea, off the Yemeni coast, 2 new islands were built by eruptions early in the 2010s, added to a small existing archipelago, and have since been slowly cut back by the waves. The pattern that emerges from these accounts is straightforward. What decides whether a newborn island lasts is not the size of the eruption, but the material it leaves at the waterline, and whether lava or the slow cementing of ash into tuff arrives before the first heavy season of swell. Distance from other land can be measured, and once it is measured, it can be ranked, which is why the question of which island lies furthest from any neighbor has a settled answer rather than an argued one. The method is simple enough in principle, since it requires only the coordinates of a shore and the coordinates of every other shore, with the shortest of those figures taken as the island's isolation. 2 different rankings come out of it, depending on whether the nearest land may be any land at all, including uninhabited rock and ice-covered coast, or must be a place where people live. The first list is headed by an island in the South Atlantic that almost nobody has stood on, and the second by a small volcanic group whose inhabitants number in the low hundreds. Ouverture sits near 54 degrees south and a little more than 3 degrees east, a rounded mass of some 49 square kilometers with sheer cliffs on most sides and glacier ice over roughly 9/10 of its surface. The nearest land is the Antarctic coast of Queen Maud Land, more than 1,600 kilometers to the south, and the nearest other island lies over 1,000 kilometers away in the opposite direction. Jean-Baptiste Charles Bouvet de Lauzier, commanding 2 French ships sent south to look for a southern continent, sighted its northern headland on the first day of January in 1739, could not land through the fog and the swell, and named what he had seen Cape Circumcision after the feast day. His latitude was close to correct, because latitude in the middle of the 18th century was a solved problem, obtained from the height of the sun at noon with a quadrant and a table. The longitude was wrong by several degrees, and since a degree of longitude at that latitude spans about 65 kilometers, the error was enough to hide the island completely. Ships that went looking for Cape Circumcision on the strength of that report found open water, and one of those ships belonged to James Cook, who crossed the region twice during his second voyage and came away doubting that any land existed there, suspecting that the French had charted an iceberg. Rediscovery came in 1808, when James Lindsay, master of a British whaler, saw the island and recorded a position much nearer the truth, though he did not get ashore. A landing was made in 1825 by a sealing captain named Norris, who called the place Liverpool Island and reported a second island to the north that no later ship ever found. Norwegian expeditions landed in the 1920s and the island was claimed for Norway, becoming a dependency, and its coordinates have since been settled to within meters by satellite methods, on a coast where landing still depends on the weather of the day. The wider difficulty behind Bouvet's misplacement occupied the maritime nations for most of the 18th century. Comparing local time aboard a ship with the time at a reference meridian gives the longitude directly. Since the Earth turns 15 degrees each hour and 4 minutes of clock error corresponds to a full degree of arc. But keeping reference time at sea meant either a clock that could survive months of damp, heat, and pitching, or a celestial method that needed no clock at all. The celestial route was the method of lunar distances, in which the angular gap between the moon and a chosen star or the sun is measured with a sextant and compared against pre-computed tables, and it became practical for ordinary navigators after the British Nautical Almanac began publishing those tables from 1767. Mechanical timekeeping arrived along a parallel track through the sea clocks of John Harrison and the trials organized by the Board of Longitude, and through the copies and improvements that followed. Cook carried a watch made by Larkham Kendall on the model of Harrison's fourth timekeeper during his second voyage, along with 3 by John Arnold, and the Kendall watch kept a steady enough rate across 3 years of Pacific and Antarctic sailing to place coastlines within a few kilometers of their true meridians. Positions taken by lunar distance improved with practice and with better sextants, and the two methods checked each other. The observations correcting the drift of the watch, and the watch filling the many nights when cloud or a young moon made the observations impossible. Kerguelen entered the charts under both methods and under a considerable misunderstanding. Yves Joseph de Kerguelen-Tremarec, sailing from the Île-de-France with 2 vessels, sighted the group on the 12th of February in 1772, was kept off the coast by fog and returned to Europe, describing what he took to be the northern edge of a fertile southern continent. A boat from his companion ship did reach the shore and take formal possession. A second voyage, larger and better provisioned, showed him a treeless archipelago of rock, bog, and glacier. And when Cook arrived in 1776 and worked along the same coasts, he called them the Islands of Desolation, a name that survived for a long while alongside the discoverer's own. The group is larger than its reputation suggests, with a main island of about 6,600 square kilometers, some 300 smaller islands and islets around it, deeply cut fjords on the eastern side, and a high point at Mount Ross, rising past 1,800 meters. Heard Island lies roughly 450 kilometers to the southeast, and beyond that, the nearest continental shore is thousands of kilometers off in any direction, with the westerly winds running unobstructed around the latitude. A French scientific station was established at Port-au-Français in 1950, and the archipelago has been occupied continuously since by rotating crews rather than by settlers. Tristan da Cunha was sighted in 1506 by a Portuguese fleet, and the island took the name of the navigator who reported it, though the surf and the cliffs kept his crews from landing. St. Helena, the closest inhabited land, lies about 2,400 kilometers to the north. The South African coast is some 2,800 kilometers east, and South America more than 3,000 kilometers west. The island is a single volcanic cone, its summit past 2,000 meters, with a narrow shelf of low ground on the northwest side, where the settlement of Edinburgh of the Seven Seas stands. A British garrison was placed there in 1816 and withdrawn the following year, and a Scottish corporal named William Glass remained with his family, which is the origin of the present community. Volcanic activity beside that settlement in 1961 forced the evacuation of the whole population to England, and most of the islanders returned within 2 years to rebuild on the same narrow plain. Their neighbors in the group are Inaccessible Island and the Nightingale Islets a short distance away, with Gulf Island some 400 kilometers to the south-southeast, staffed by a weather party and otherwise left to its birds. Rapa Nui, the island Europeans call Easter, lies about 1,900 kilometers east of the nearest inhabited neighbor in the Pitcairn group and roughly 3,500 kilometers west of the Chilean coast. and it had been settled by Polynesian voyagers many centuries before any European chart carried it. Jacob Roggeveen, sailing for a Dutch company, came upon it on Easter Sunday in 1722 and gave it the name that stuck in Europe. A Spanish expedition from Peru under González de Haedo arrived in 1770 and claimed it. Cook anchored there in 1774 and reported the island's poverty of water and wood, and Chile annexed it in 1888. Its longitude, disputed among the early accounts, was settled as chronometers spread through the Pacific trade. Between these scattered points, the ocean reaches its greatest distance from any coast at a position in the South Pacific, near 48 degrees south and 123 degrees west, where the three nearest pieces of land are an islet off Easter Island, an atoll at the eastern end of the Pitcairn chain, and an ice-covered island on the Antarctic margin, each about 2,600 kilometers away. No land breaks the surface there, and the seafloor lies several kilometers below, which makes the spot a measured absence rather than a discovery, arrived at by calculation once every shoreline in the hemisphere had finally been placed. Sailors who put ashore on small oceanic islands for water and firewood often carried away specimens that no one at home could match to anything, and by the middle of the 19th century, the pattern inside those collections had become firm enough to state as a rule. The smaller and more isolated a piece of land, the greater the share of its plants and animals that live nowhere else on Earth. Naturalists called such species endemic, meaning native to one place and to no other, and the word came to carry a quiet caution with it, since a beetle or a shrub restricted to a single ridge of a single island can be lost through an accident that would hardly be noticed on a continent. Aboard the Beagle in 1835, Charles Darwin was told by an official of the small Galapagos settlement that the giant tortoises differed from island to island, and that a practiced eye could name the island a shell had come from. He collected mockingbirds separately by island and noticed that they too varied from one to the next, though he labelled his finches loosely and later regretted it. And it was John Gould, working through the skins in London in 1837, who sorted them into a group of closely allied but distinct species with beaks of markedly different shape and depth. Domed shells belonged to the wetter, higher islands where grazing was low to the ground, while the saddle-backed form, with its raised front rim allowing the neck to reach upward, belonged to drier ground where food hung above the animal's head. Giant tortoises had once been common across the western Indian Ocean, on Mauritius and Rodriguez and Réunion and the granitic Seychelles, and ships' crews took them by the hundred as living provisions that needed no feeding on a long passage. By the 1800s, only Aldabra, a raised coral atoll of jagged limestone with almost no standing fresh water and few easy landings, still held a wild population of any size, its awkwardness having served it better than any law. In the 1870s, a group of naturalists, Darwin among the signatories, petitioned the colonial administration in Mauritius to protect what remained, and the population there has since been counted in the tens of thousands, the largest anywhere. Aldabra also keeps the last flightless bird of the region, a rail whose wings no longer carry it, surviving on islets that rats have not reached. Alfred Russel Wallace set out the underlying logic in island life, published in 1880, by dividing islands into two kinds according to their history rather than their appearance. Continental islands, cut from a mainland by rising water, retain a sample of that mainland's inhabitants, mammals and frogs and freshwater fish included. Oceanic islands, raised from the sea floor and never joined to anything, receive only what can arrive across open water, which means birds, bats, flying insects, seeds carried in mud, on a bird's foot or in its gut, spores lifted high on wind, and whatever survives a voyage on drifting timber. Native land mammals other than bats are generally absent from them, and amphibians almost entirely so. And that filter, applied over long spans of time, shapes the whole roster of what an island contains. Thomas Vernon Wollaston, cataloguing the beetles of Madeira in the 1850s, found that a striking proportion of the endemic species had lost the use of their wings, and Darwin took up the observation and turned it over at some length, weighing whether an insect that flies on a windy island is simply swept out to sea and removed from the breeding population. The same reduction appears again on the subantarctic islands, where flies and moths peculiar to Kerguelen and the Crozet group have wings shortened to stubs or nearly absent, and where much of the insect life spends its time inside cushion plants and under stones rather than in the air. Whether constant wind is the whole explanation remains open, since flightlessness also saves the cost of building and running wing muscles in a place with little to fly toward. Joseph Hooker, botanizing on Kerguelen during the Ross expedition in the Erebus and the Terror in the early 1840s, described a cabbage-like plant with a thick stem and coarse leaves that grows on those islands and nowhere beyond them, and a few neighboring groups of the same latitudes. Sealers had already been eating it against scurvy, which gave it its species name, and Hooker noted the feature that made it interesting to a botanist. Its flowers are dull, unscented, and built for the wind. In a place where flying pollinators are scarce to the point of absence, a plant of that kind cannot spread to the next island unless its seed makes the crossing, and so it stays where it is indefinitely. Socotra, lying off the Horn of Africa in the Arabian Sea, holds the dragon's blood tree, whose branches divide again and again into an upturned crown that from a distance looks like a stiff green umbrella, and whose red resin gave the tree its name and its old value in trade. Isaac Bailey Balfour reached the island in 1880 and returned with a collection that became the first thorough account of its flora, and later work has put roughly a third of the island's plant species in the category of occurring only there, among them a swollen trunk tree that is the sole tree in the cucumber family. Most of the dragon's blood groves sit on higher limestone ground where cloud drifts through, and the trees comb moisture from that mist onto their own root ground below. A related species grows in the Canary Islands, and Alexander von Humboldt, stopping at Tenerife in 1799 on his way to the Americas, made a point of visiting the old dragon tree at Orotava, measuring its hollow trunk and reflecting on its probable age. That particular tree came down in a storm in the 1860s, though others remain on the islands, and the species has become one of the standard examples of a plant confined to a single archipelago and its immediate neighbors. Hawaiian plants push the pattern further than almost any other flora, with something close to 9 in 10 of the native flowering species restricted to the archipelago, and a good many of those to one island, one valley, or one lava flow of a certain age. The silver swords, rosettes of narrow silvery leaves that flower once and then die, include forms limited to the upper slopes of a single volcano, and the Hawaiian lobelioids produce dozens of species with curved tubular flowers matched to the curved bills of native honey creepers, themselves a set of birds descended from a single finch-like colonist. Botanists working the leeward gulches in the 20th century repeatedly found populations of a few dozen individuals whose whole world range was a stretch of cliff a few hundred meters long. St. Helena in the South Atlantic illustrates both halves of the subject at once. Having lost much of its original vegetation to goats and timber cutting before anyone described it, while later surveys of its invertebrates listed hundreds of species known from that island alone. The St. Helena ebony, a low shrub with white flowers, was believed gone for well over a century, until two surviving plants were located on a cliff face in 1980, from which cuttings were taken and grown on. A large flightless earwig peculiar to the island was last recorded in the 1960s, and searches since have not produced a living one. On Lord Howe Island, off eastern Australia, a heavy flightless stick insect vanished after rats came ashore from a grounded steamer in 1918, and it was written off until climbers on Ball's Pyramid, a bare rock stack some kilometers to the south, reported dead specimens. An expedition in 2001 found a small living population beneath one shrub on that stack, and captive lines were established on the mainland from a very few founders, which is the ordinary shape of such work. Narrow ground searched slowly, a species held by a thread, and an inventory of island life that botanists and entomologists are still adding to valley by valley. For as long as coastal outlines have been engraved and printed, sea charts have carried a small number of islands that no second vessel could find, and the ordinary fate of such a mark was to be copied forward from one edition to the next, since an engraver working in Amsterdam or London had no means of testing a report made in mid-ocean 20 years earlier, and the prudent choice, both for trade and for navigation, was to leave the island where the previous plate had placed it. Striking land from a chart demanded something firmer than a run of unsuccessful sightings. It required a ship to cross the stated position in clear weather, with the sounding line going down and coming up again from deep water, and then, ideally, a second ship to do the same. Among the longest-lived of these was Friesland, which entered European geography through a book and map published in Venice in the middle of the 16th century by a member of the Zeno family, who presented the work as a reconstruction of letters written by his ancestors during voyages in the northern seas nearly 2 centuries before. The map showed Friesland lying south of Iceland, rather larger than Ireland, its coasts crowded with bays and named harbours in the manner of a well-known place. Mercator drew it, Ortelius drew it, and lesser cartographers followed both, so that for something close to 100 years a substantial island occupied a patch of the North Atlantic where the sea floor lies thousands of meters down. Later readers came to regard the outline as a confused rendering of Iceland or of the Faroes, drawn from second-hand sailing directions and stretched to fill the space available. West of Ireland, the chart tradition kept an island called High Brasil, which appears on Portolan charts from the 14th century onward. Frequently drawn as a neat ring, divided across the middle by a strait, a shape too tidy to have come from any survey. Merchants from Bristol are recorded as having sent ships to look for it in the closing decades of the 15th century without result, and rather than disappearing, the island drifted, moving further out into the Atlantic on successive maps and shrinking as it went. Until in 19th century editions it survived only as a rock bearing a version of the old name, and was at last withdrawn when no sounding could be brought up in agreement with it. Before reliable chronometers went to sea, the arithmetic of position itself manufactured islands. Latitude came from the altitude of the sun at noon and was generally trustworthy to within a few miles. But longitude came from dead reckoning, from an estimate of speed and heading accumulated over weeks, and errors of 1 or 2 degrees were unremarkable on a long passage. A genuine island, sighted by 2 ships, could therefore be entered twice, at positions far apart, under 2 names, and a real rock could be fixed 100 kilometers from where it lay, so that later navigators searching the charted spot found open sea and reported the place as empty, while the rock itself remained a hazard somewhere else entirely. Ice contributed its own share. Tabular bergs in high latitudes present flat tops and steep white walls that resemble cliffs at a distance, and bergs that have carried away moraine from a glacier bed arrive stained with dark rock and gravel, looking from a few miles off like low ground with a beach. Fog banks standing on the horizon in still air take the profile of hills. Rafts of pumice from a submarine eruption spread across the sea in pale grey sheets that a lookout may take for a shoal. And discoloured water above a rising vent has been logged as broken ground more than once. Some reports were of things briefly present, banks thrown up and washed away again within a season. In the high Arctic, the atmosphere itself supplied convincing land. Where cold air lies against colder ice and warmer air sits above it, light bends downward as it travels, lifting distant features above the true horizon and stretching them vertically into what looks like a coast with headlands and valleys. Robert Peary reported land to the northwest from the Canadian Arctic Islands early in the 20th century, and it was entered on charts under the name Crocker Land. An expedition led by Donald Macmillan set out to reach it, travelled far out over the sea ice, and saw the hills and bays ahead of them clearly enough to be worth sketching, until the sun moved and the whole prospect dissolved into flat ice, after which the party turned back and the name was removed. Reports from the seas north of Siberia produced a comparable case in Sannikov Land, named for the hunter who described distant heights beyond the New Siberian Islands in the early 19th century. Russian and later Soviet expeditions searched by ship and eventually by aircraft, and after systematic flights over the region in the 1930s, the conclusion was that nothing solid stood there. Whether Sannikov had seen a mirage or an island that no longer existed remains open, because that coast holds ground made largely of ancient ice bound with silt, and 2 islands of this kind in the same waters were watched through the 19th and early 20th centuries as the sea cut them back year by year until each was gone, leaving a shoal where a surveyed island had been. Southern waters kept their own doubtful entries for generations. A ship on Frobisher's 3rd voyage came home in 1578, reporting land in the North Atlantic between Friesland and Ireland, and that report, under the ship's name, held its place on charts for the better part of 2 centuries. first as an island, then as a shallow bank, then as sunken ground, each demotion recording another failed attempt to find it. Near Bouvet, in the far South Atlantic, a sealing captain described a second island in the 1820s, and it stayed on the plates until a German oceanographic expedition at the end of the century ran soundings through the area and found only deep ocean. South of New Zealand, 2 islands reported by whaling and sealing masters were hunted by vessels bound for the Antarctic in the early 20th century and never confirmed. Hydrographic offices met this inheritance with notation rather than deletion, and the abbreviations they adopted are still printed on paper charts, marking a feature as reported, its position approximate, or its existence doubtful. A doubtful island could then be carried honestly, as a warning rather than a fact, until survey work caught up with it. That work advanced by lines of soundings run across the suspect ground at intervals, by wire drag sweeps in coastal water where a launch towed a wire at a set depth between 2 boats to catch any pinnacle, and from the 1920s by echo sounders that drew a continuous profile of the bottom beneath a moving hull instead of a scatter of separate measurements. Satellite measurement of sea surface height completed the argument at a coarser scale, since a large mass of rock standing up from the abyssal plain pulls water toward itself and raises the ocean surface above it by a small but measurable amount, a bulge of a meter or so over a substantial seamount. Maps of the sea surface built from radar altimetry therefore show where big undersea mountains rise, and an island-sized feature within reach of the surface cannot be absent from that record, although a narrow pinnacle can still escape it and be found the hard way by a hull. In November of 2012, an Australian research vessel working in the Coral Sea between Queensland and New Caledonia crossed the charted position of Sandy Island, an elongated shape that had appeared in various datasets and in widely used mapping software, and recorded around 1,400 meters of water. French charts covering those waters had already dropped it, and the surviving shape appears to descend from a 19th century sighting copied into one general chart, and from there into the digital coastline files that later software inherited without question, which is how an island removed in one archive can persist in another for a century and more. During the Second World War, a geologist named Harry Hess commanded a naval transport in the Pacific, and on the long crossings between islands, he left the ship's echo sounder running, recording the profile of the seabed beneath a vessel that was going where the war sent it, rather than where a survey would have gone. Among the traces he collected were undersea mountains that did not end in peaks. Their summits were flat, cut off cleanly, and they stood several hundred to some 2,000 meters below the surface. He gave them the name Guyots after Arnold Guyot, a Swiss-born geographer who had spent his later career at Princeton, and in 1946 he described them in print as drowned ancient islands. A level platform at the top of a volcanic pile is difficult to produce anywhere except at sea level, where waves working on a rock coast grind the land down to a stump and leave a bench of truncated rock behind. That is the reading Hess proposed, and it has held. The flat surface is a beach planed across a former island, and the depth at which it now sits is a measure of how far that island has sunk since the waves finished with it. He suspected at first that the drowning had happened in the remote Precambrian past, before reef-building organisms existed to build upward and keep pace, which turned out to be too early by a wide margin. Cories taken from Guyot summits in the western Pacific settled the age question. Beneath a thin cap of deep-sea ooze, drills recovered limestone full of shallow water organisms, including the thick-shelled bivalves that built reef frameworks in the Cretaceous, together with rounded volcanic pebbles of the kind that collect on a beach and traces of soil formed in open air. The material was laid down within reach of sunlight and surf, and it now lies a kilometer or more down, which fixes both the former existence of the island and the amount of subsidence since. Fossil ages clustered in the middle of the Cretaceous for many of the western Pacific examples. Cooling accounts for the descent. Oceanic crust forms hot at a spreading ridge, thickens and grows denser as it loses heat, and sinks steadily lower as it ages and moves away, so that a volcano built on young crust rides down with the plate that carries it. Whether the resulting feature becomes an atoll or a guyot depends on a competition between that slow lowering and the upward growth of reef organisms living on the summit. Where growth kept up, a ring of limestone remained at the surface. Where it failed, through cooling water, a change in nutrients, a period of sinking too rapid to match, or simple bad luck, the platform went under and stayed under. Along the Emperor Chain north of Hawaii, the failure is systematic, since the plate has been carrying those seamounts steadily poleward for tens of millions of years, out of the warm belt where reefs can grow at all. Drilling on several of them brought up basalt weathered in open air, and sediments deposited in shallow lagoons, so the northern emperors were islands in their day, with beaches and rain and running water, before they subsided and passed into water too cold for anything to build them back up. Their summits now lie well below the surface, arranged in the same order of age that the volcanic chain shows above water. Closer to the continents, the drowned ground is of a different kind and a far younger age. Continental shelves are not deep ocean at all, but the submerged edges of the land masses, and during the height of the last glaciation, when a great volume of water was locked into ice sheets, sea level stood roughly 120 meters lower than it does now. The shelves were dry. Borneo, Sumatra, and Java stood joined to the Asian mainland across the exposed Sunda Shelf. New Guinea and Tasmania were part of Australia. Britain was a peninsula, and a broad plain connected Siberia to Alaska, where the Bering Strait now runs shallow and cold. Fishermen working the southern North Sea encountered the evidence long before anyone assembled it into a landscape. Trawls came up with lumps of compressed peat, which the crews called moorlog, along with the bones and teeth of mammoth, reindeer, bison, and horse, animals of open ground rather than of the sea. In the early 1930s, a trawler working the banks off the Norfolk coast brought up a barbed point made of antler, a hunting implement, from water that had been dry land when it was made and lost. Archaeologists later gave the drowned country the name Doggerland, after the Dogger Bank that is one of its surviving high spots. Seismic data gathered by the oil industry turned that scatter of finds into a map. Three-dimensional surveys shot to image the rock kilometers below also record the shallow layers immediately beneath the seabed, and within those layers lie the channels of rivers, the basins of lakes, the low ridges of hills, and the outlines of a large estuary system, all buried and preserved rather than erased. Reworking that archive, researchers traced a countryside of valleys and marshes across an area comparable to a modest nation and dated its flooding to the millennia of meltwater rise that followed the retreat of the ice. A drowning gradual enough to be lived through and permanent nonetheless. Southeast of Asia, the same story is legible in the sonar record, where the drowned courses of large rivers run for hundreds of kilometers across the Sunda Shelf toward the deep water, gathering tributaries that now discharge separately into shallow seas. Elsewhere, the mark left by lower sea levels is a terrace or a notch cut into a submarine slope at a consistent depth. A coastline preserved as a step. Off the flanks of the Hawaiian Islands, drowned reefs lie in a series of such steps, their depths reflecting both the rise of the ocean and the sinking of the volcanic load beneath them, which makes them useful for measuring each process against the other. Wire soundings could never have found any of this. A single deep measurement with a weighted line took hours of paying out and hauling in, and the great 19th century expeditions returned with a few hundred depths to describe the whole world ocean, enough for the broadest outline and no more. Acoustic sounding, developed in the years after the First World War, replaced the wire with the travel time of a pulse of sound, and a German expedition working the South Atlantic through the 1920s brought home soundings in the thousands, a continuous profile rather than a string of dots. Every ship fitted with the instrument became a surveyor while it was simply going somewhere. Multi-beam sonar, which fans out a spread of beams across the track, instead of one directly beneath the hull, converted those lines into strips of mapped ground, and the strips into topography with slopes and craters and landslide scars. Counts of seamounts rose from hundreds to tens of thousands as the coverage grew, and among them the flat-topped ones stand out in the data as clearly as they did on Hess's paper rolls. Only a modest fraction of the sea floor has been surveyed this way, so the tally of drowned islands remains open, and features the size of a small country's worth of former land are still being added to the charts. Naming falls to the surveyors, since these places lost whatever names they may once have carried, if anyone was alive to give them any. Aguyo in the North Atlantic west of the Canaries takes its name from the research vessel that found it, and many Pacific examples honor ships, scientists, or the languages of nearby archipelagos. The islands themselves had rock coasts, freshwater streams, plants and animals brought by wind and current, and in some cases fringing reefs, all of it now some depth of water below the keel of anything passing overhead, indistinguishable from open sea to a passenger at the rail. Cameras carried aloft changed the work of drawing a coast more completely than any instrument since the chronometer, because a photograph taken from a few thousand meters records the whole shape of a bay at once in a single instant, with every headland and sand spit in fixed relation to every other. Coastal survey by boat had always been a matter of assembling a line from separate positions, each one earned by a sight of the sun or a bearing on a hilltop, and the line was only as good as the weakest link in that chain. From the air, the chain shortened. A pilot flying a straight course while a camera in the floor of the aircraft exposed plates at regular intervals produced a strip of overlapping pictures, and where the overlap was sufficient, the same stretch of shore appeared on two frames taken from different points in the sky. Two photographs of one piece of ground viewed together in a plotting instrument yield relief as well as plan. Photogrammetry exploits the small differences between the two images, the parallax that shifts a cliff top further than a beach, to give heights as well as horizontal positions, and by the 1930s, the technique had become the standard method for mapping country that no surveyor had walked. Ground control was still needed since photographs alone float free of the Earth without at least a few points whose latitude and longitude are known by other means. Expeditions to Greenland, to the Canadian Arctic, and later to Antarctica therefore combined flying with landings, setting a handful of astronomical stations along a coast, and letting the photographs fill everything between them. Cloud remained the constant obstacle, and in high latitudes it was joined by low sun angles that threw long shadows across the very ground being mapped, by sea ice that hid the line between water and shore, and by snow cover that erased the contrast a lens depends on. Flying seasons were short. Oblique photography helped, with cameras aimed sideways as well as straight down so that a single pass could sweep from horizon to horizon. And the wartime configuration of 3 cameras used together, 1 vertical and 2 oblique, gave the broad coverage that post-war Arctic mapping was built on. Accuracy suffered towards the edges of such pictures, but for a coastline never recorded at all, an approximate line was a considerable advance. In Fox Basin, the western arm of the waters between Baffin Island and the Canadian mainland, air photographs taken in the late 1940s revealed land that no chart had shown. Prince Charles Island, larger than several well-known island nations, had lain there among shallow, ice-choked water, low and flat, and easily mistaken from a boat for the general whiteness of the basin. And a smaller neighbor was identified in the same surveys. Both were among the last islands of any size to be added to the world's inventory, and neither was found by a landing party. They appeared as shapes on film, and the field visits came afterwards to confirm what the interpreters had already outlined. Radar answered the cloud problem by working at wavelengths that pass through it. Side-looking airborne radar, developed for military reconnaissance and adapted for survey, sends pulses out to one side of the aircraft and builds an image from the timing and strength of the returns, so that the picture is made of roughness and moisture and slope rather than of light. Water, being smooth at these wavelengths, reflects the pulse away from the antenna and comes back dark, while land scatters it in all directions and comes back bright, which makes a shoreline stand out with a sharpness that optical imagery rarely achieves. Synthetic aperture processing, in which the motion of the platform is used to imitate an antenna far longer than any that could be carried, sharpened the result further. A short-lived satellite launched in 1978 carried the first civilian instrument of this kind into orbit. And although it operated for only about 3 months, it demonstrated that coasts and ice edges could be imaged from space in any weather and in the dark. Optical satellites arrived earlier in continuous service, beginning with the first of the Landsat series in 1972, and their contribution was less about fine detail than about uniform coverage of everything. Ground resolution was coarse by later standards, tens of meters to a pixel, yet a small island in an empty sea is a strong signal even in coarse data. And one such object was noticed off the Labrador coast in the mid-1970s on imagery from the program. A helicopter flight confirmed a real rock where the pixels had suggested one, and the feature took its name from the satellite that found it, a small island named after a machine in orbit. Cases like it were not numerous, since ships had already been almost everywhere, but they showed that the inventory had not been closed. Where the water's edge should be drawn turned out to be a harder question from orbit than from a boat. A satellite records the sea surface as it stood at the moment of the pass, which is some arbitrary stage of the tide, and a mosaic assembled from many passes therefore stitches together many different tidal states so that an image-derived shoreline can wander seawards and landwards for no reason connected with the land. Mapping agencies handle this by defining their coastline against a chosen datum, commonly mean high water, and by correcting or selecting images to match, which requires tide models for places where no gauge has ever been installed. Resolution matters as well, because the finer the data, the more small rocks and channels appear, and a channel decides whether one island is two. Counts of islands published by countries with intricate coasts, Finland and Sweden and Norway among them, rose sharply when their shorelines were digitized at fine scales. Not because new land had formed, but because the measuring instrument had grown more discriminating. Beneath the Antarctic ice sheet, radar of a different kind found coasts that no water has touched for millions of years. Radio waves at long wavelengths penetrate cold ice and reflect from the rock beneath, so an aircraft flying a grid at constant height can record the thickness of ice below it, and, by subtraction, the shape of the bed. Decades of such flights, compiled with satellite measurements of the upper surface, produced maps showing that much of West Antarctica rests on ground far below sea level, and that if the ice were removed and the sea allowed in, a good deal of the region would stand as an archipelago of separate islands rather than a single land. Greenland's bed, mapped the same way, holds a long trough system and its own drowned interior, with high rims near the coasts. Along the east coast of Greenland, ice retreat has converted several supposed peninsulas into islands within the span of ordinary map revision. A body of land near Liverpool Land was shown in the early 2000s to be separated from the mainland by a channel that a shrinking glacier had uncovered, and it acquired a Greenlandic name meaning the warming island. Comparable changes have been reported in Svalbard and in the Russian High Arctic, where survey teams and satellite comparisons have identified small islands emerging from beneath thinning ice caps and from behind retreating glacier fronts. North of Greenland, gravel banks lifted and shifted by sea ice have repeatedly been put forward as the northernmost land on Earth, and their standing changes as new visits find some of them gone and others newly built. Every shoreline in the modern inventory therefore carries a date, and the date matters. Coasts drawn from photographs flown in the 1950s differ from coasts drawn from radar in the 1990s. And both differ from what the current instruments record, partly because the measuring has improved and partly because the land and the ice and the water have moved. We are going to stop here. The music will carry on for a while, and then it will fade on its own. There is nothing more to do tonight. Rest well and see you very soon.